we are from Group 4. We will present about the heat and mass transfer project for question number 2. And my name is Nofara Aini binti Salbi, and my metric number is 198226.
My name is Nur Iman Zulika binti Zamri and my metric number is 198421.
My name is Muhammad Afif bin Roslan Asikin, metric number 199027.
My name is Siti Nur Afika binti Muhammad Ghani, metric number 197702.
So for the introduction of heat and mass of the heat exchanger is a device that transfers thermal energy between two or more fluids in thermal contact and at different temperature. And the transmission of heat from one side to another for heating and cooling in heat exchanger is known as heat transfer. So engineers in industry often find themselves in position to select the heat exchanger accomplished with certain heat transfer tasks, such as to heat or cool a certain fluid to a desired temperature. The proper design or selection is depend on several factors, such as heat transfer rate, construction type, materials, and pressure drop and cost. There are two main types of heat exchanger. First is the shell and tube heat exchanger. Shell and tube heat exchanger consists of shell on the inside of the heat exchanger, shell on the outside of the heat exchanger, and tubes at the inside of the heat exchanger. And the second type is plate heat exchanger, which consists of a set of plates contain of heat, hot and cold fluid. So for our question for group 4 is, a shell and tube heat exchanger is to be designed to heat up water at a rate of 18,000 kg per hour from 25 degrees Celsius to 45 degrees Celsius. Hot water at a rate of 14,000 kg per hour flow through one shell pass at 80 degrees C and act as the heating fluid. It is desired to limit the tube length below 2.5 meter because of space limitations in the plant. So as an engineer, you are desired to evaluate your design by identifying what configurations and features could be explored in heat exchanger to satisfy the space constraints. To estimate the magnitude of fouling factor, if with usage the outlet tube stream temperature found to decrease by 33 degrees C due to deposition of solid on tube surface. So specification for our shell and tube heat exchanger is inner diameter of tube is 1.9 cm. Number of tube is 40 tubes, and average shell side heat transfer coefficient is 2,994 watt per meter square Kelvin. So I'll pass to our next presenter.
Okay, so this is the schematic of the process. There are a few suggestions of design that we propose. The first design is double pipe counter flow heat exchanger. The second design is multi-pass heat exchanger parallel flow. It consists of two tubes and one shell. And the third design is multi-pass heat exchanger counter flow. It also consists of two tubes and one shell. Next. So this is the fluid properties used for the calculation. The temperature, the inlet is 25 for cold water and for hot water it's 80. For temperature outlet, the cold water is 45 degrees C and the hot water is to be determined. Next is specific heat capacity. For water, it's 4,180 for both cold and hot water. And then mass flow rate for cold water is 18,000 kg per hour, which we convert to kg per second equals to 5 kilogram per second. Next is hot water, which is 14,000 kilogram per hour. And when it's converted to kilogram per second, it is 3.889 kilogram per second. So the given diameter of the inlet is 1.9 cm and the desired length is less than or equal 2.5 meter. So this is the fluid properties used for the calculation. For density of water at 25 degrees C is 997 kilogram per meter cube. Viscosity is 0.891 times 10 to the power of negative 3 kilogram per meter second. The thermal conductivity is 0.607 watt per meter Kelvin. And lastly, Prandtl number is 6.14. So for the first design, we assume, we make some assumption, which is it is a steady operating condition. The second assumption is the heat exchanger is well insulated so that the heat loss to the surrounding is negligible, and thus heat transfer from the hot fluid is equal to the heat transfer to the cold fluid. Next, the third assumption is changes in the kinetic and potential energies of fluid streams are negligible. And the last assumption is fluid properties are constant. Next, for the second design, we assume that it is steady operating condition exists. The heat exchanger is well insulated so that heat loss to the surrounding is negligible, and thus heat transfer from the hot fluid is equal to the heat transfer to the cold fluid. Changes in the kinetic and potential energy of fluid streams are negligible. There is no fouling. The flow is fully developed. Fluid properties are constant. The thermal resistance of inner tube is negligible since the tube is thin wall and highly conductive. And last assumption is heat exchanger with parallel flow. For the third design, it is also the same. Steady operating condition exists. It is also well insulated, and the next the changes in the kinetic and potential energies of fluid streams are negligible. There is no fouling. The flow is fully developed. Fluid properties are constant. The thermal resistance of the inner tube is negligible since the tube is thin wall and highly conductive. And last one is heat exchanger with counter flow. The tube is assumed to be thin and therefore area can be neglected, which is D outlet equals to D inlet, and R wall is also neglected. So this is the list of equations that we use in the calculation. So I'll pass to the next presenter.
Okay, thank you, Iman. For next part is choosing the type of heat exchanger. Next part, please. Okay, choosing type of heat exchanger. For the first D, we have to calculate the velocity, the Reynolds number, Prandtl number to know what type of the fluid is it. For this question, we have know that the fluid is turbulent. And after that, we have to calculate the HI and also the U for the heat exchanger. If our HI is 2290 watt per meter cube K, and the U is 1297 watt over m squared per K. And our rate for the heat exchanger is 418,000 watt. And from this, we can find the theta T LM, which is the first of all, we have to find the theta H, and also the we have to find first the TH out, because from the question we do not know the TH out. So the firstly we have to find the TH out, and from the equation given, we get the TH out from the equation is 54.3 degrees Celsius. Next slide. Okay, after we get all the information that not given at the first place, we can continue to find the length for every design. We start with the first design, which is double pipe and counter flow heat exchanger. This is the graph for the double pipe counter flow heat exchanger. From this, firstly we have to find the TLM, theta TLM. So the TLM for this heat exchanger is 32.07 degrees Celsius. And after we have find the theta TLM, we find the area surface of the heat exchanger, and we got it 10.05 meter square. And after that, we assume that the heat exchanger have one shell and one tube pass. Therefore, we can get the L is 4.21 meter, and this length is actually greater than 2.5 meter. So we cannot use this design. So we move to the next design, which is multi-pass and parallel flow heat exchanger. So this is the graph for multi-pass and parallel flow heat exchanger. The same thing for the multi-pass, you find the theta TLM CF, and you got it 25.71 degrees Celsius. And for this part, we also have made the assumption that this part have the falling factor. Therefore, we have to find the falling factor by using this expression. And from the table, from the figure that we get from the textbook, we can get the falling factor is 0.95. Sorry, the friction, not falling factor, sorry. After that, we can find the area surface by using this equation, and then we get the area surface is 13.189 meter cube. We assume for this exchanger is one shell, two tube pass, and we got the length for the heat exchanger is 2.76 meter. However, this length also greater than 2.5 degrees Celsius. So we can't use this design. Next slide. Therefore, we try with the third design, which is multi-pass and counter flow heat exchanger. The same thing again, we got the theta TLM CF, which is 32.07 degrees Celsius. And we find the F, which is 0.95. And then we find the AS, which is 10.57 meter cube. And for this part, we divide the area surface with the end pass, which is actually this one is the same with this equation, but we simplify it and we get the value is 5.287. Therefore, the length for the heat exchanger is 2.214 meter, and this length is actually less than 2.5 meter. So we can use this design as our heat exchanger to be chosen as our desired heat exchanger that have achieved the space constraint. I will pass to the next presenter. Thank you.
Okay, thank you, Afiq. So next is for the question number 2. Based on the question, the magnitude of falling factor RF on the heat exchanger C, which is the third one, we need to find the new Q, heat transfer, and also temperature, hot out, and also mean load temperature, and U, overall heat transfer coefficient. So the properties that we have is the temperature in the properties that we have is the temperature inlet for the cool and also for the hot water, and the temperature outlet for the cool water, specific heat capacity, and also mass flow rate. So the first thing is we have to find the Q, heat transfer coefficient, heat transfer. Okay, we know that Q equals to Q cool equals to Q hot. So to find the Q, we can use the equation mCp delta T. Since we have all the value for the cool fluid, so we use cool mc Cp delta Tc. So we get the Q is 300 watts. And then we can find delta H, the same equation. Delta H we will get 21.9 degrees C, but in this slide we don't write it. So after we know the delta T hot, we can find the temperature hot outlet, which is 80 minus 21.9, and we get 58.1 degrees C. So next, we need to find delta TLM, and this is the plot for the multi-pass counter flow. To find the delta TLM, we can use this equation and calculate for the delta T1 and delta T2 and substitute in equation 11.25, and we get 35.49 degrees C. So next, we need to determine the correction factor. So to determine the correction factor, we can use figure in textbook, figure 11.9. But before that, we must calculate the value for P and R and read from the figure, and we get the correction factor 0.97. And then we can find overall heat transfer coefficient U using equation Q equals to UAF delta TLM. Calculate the area first, and then the area is 10.57 since it's a tube. Then we can calculate next. We can calculate the value of U. We get 976.433. And then we can find the following. We can use this equation 11.18 to find the Pauling factor 0.000255. So Pauling factor for the double and counter, we can see that is smaller than Pauling factor for multi, fast and parallel. So from the result, we can see that type C has the length that is smaller than the limitation length 2.5. So C is the best design for our limitation. So next is the design evaluation by identifying what configuration and features. So from our calculation, we find that counterflow arrangement exhibit the highest efficiency. Multipass offer great flexibility for optimizing fluid velocity, pressure drop, and heat transfer. Minimize potential fouling, which cause the loss its thermal and hydraulic performance. Before reaching the output valve, the fluid flow on the tube side of a heat exchanger can make 1, 2, or more passes. When there are 2 or more passes inside the heat exchanger, the available space for each pass is limited. Then flow speed increase and more heat exchange is generated. And then next, so this is the final heat exchanger design specification that we choose, which is the third design. So I will pass to the next presenter.
So I will explain about the reason for using more than one tube pass. First, it will provide larger surface area. Uh, the number of tube pass can help to transfer heat rapidly, and it will improve the heat capacity of the heat exchanger, and also increase the overall heat transfer coefficient to the system so that the heat can be transferred faster and reduce the air gaps. Like the equation below, Q is equal to U, which is the overall heat transfer coefficient, times with surface area times with the temperature difference. So heat transfer rate is directly proportional to the overall heat transfer coefficient. So the second is no air gaps flowing inside the tubes. So since air has a low thermal conductivity, the rate of heat transfer will be slower. Thus, the inside the tube, we need to make sure the fluid inside the tube. We need to make sure that only fluid is flow inside the tube, and there is no air gaps. Hence, because the air gaps will reduce the effectiveness of heat exchanger. And the next is temperature difference between hot and cold fluid, which is the temperature of cold fluid must be always lower than the hot fluid because it can extract more heat from the hot fluid than the coolant with higher temperature. Hence, it will provide more effective heat transfer to the heat exchanger. So for the conclusion, our chosen heat exchanger is a design tree, multi-pass with counter flow arrangement, because the flow arrangement of shell and tube heat exchanger chosen is counterflow because it gives the best efficiency to heat exchanger, and the fouling factor also can be minimized when choosing the correct heat exchanger configuration. And lastly, for the multiple number of tubes used provide large surface area to the heat exchanger so that the heat can be transferred faster and efficiently. The temperature difference between the hot and cold fluids also define on how the heat exchanger can work well. So that's all from our group. Thank you.